Hello friends, welcome back. Now today we will be discussing on how to prove a particular language is a non-context free language using pumping lemma for context free languages. So just begin. So this is what we are dealing with today. So the unit number 6, context free languages and non-context free languages. Within this, pumping lemma and examples. So let's begin. So the heading is pumping lemma for context-free languages. Now you would be very uh, coming to this word pumping lemma for the first time. So let me clarify what pumping lemma is exactly. So pumping lemma is exactly the essential properties of a context-free languages. For an example, if I'm talking about a particular language L, and if that language is a context free language, what I'm saying, if that language is a context free language, then that L should have all these properties explained in this pumping lemma. Okay, for an example, if I'm talking about a person, okay, if I'm talking about a person with its characteristics in simple terms, so for an example, if I'm talking about a particular person called Vikrant, and if I'm saying the Vikrant is intelligent, he is honest, he is hardworking, so all these are its characteristics, okay, by which we are recognizing Vikrant. So same terminology is true for this pumping lemma characteristics, or we are specifying pumping lemma properties for a context-free language. So if I'm recognizing a particular language, if it is a context-free language, then it must have these particular properties. Now just read what the pumping lemma is. So in this first statement, it is let L be a context-free language. So I'm considering a given language is already a context-free language, and then there is a constant n. So we are considering a particular constant n that depends on L. So let's consider a particular L which is already a context free. This is my assumption if it is okay, and I'm along with this I'm considering there would be a constant n. So what do I do with this? So the theorem says so such that that depends on L such that for all x, so what x is any particular string which has been generated or which is a part of that context free language L. So I'm considering this as a context free language, or considering for all such strings x, okay, which belongs to this L. And what is the constraint over this? Let the length of this string x is always greater than what the constant is. So we have thought for a constant, so always look for the length of the string which is greater than or equal to this given constant, which depends upon L. So depending upon the language changes, this constant may change. So this n is depends upon this L. Now what next property is, so there exists a particular substring u v w x y. So this is a particular string u v w x y satisfying these three constraints. So what constraint means? See, whatever string you are thinking of x, okay, it should be composed of, so I should be able to break up that string. This x which is belongs to this L should be should consist all this 5 substring. It should be made up of this 5 substring. So substring u v w x and y. Now if you divide this x into 5 substrings that compose a particular x which is in the language, so what second condition says, if I take the length, okay, see, consider this substring v and this substring x, so together of this it should not be 0, means some elements should be present either in v or x, they both should not be null. So if I take the collaborative length of v and x, substring v and x, it should not be 0. This is the condition, next condition. What the next condition is in this particular process? So length of this middle vwx, so this, if you break up this string into any format uvwxy, uvwxy, so if I take the length of this middle vwx, okay, so that length is always should be less than what we define a particular constant n for that l. Okay, now this is the next condition number 2, where we deal with this two sub we decide we go for this length of vx, and there is a constraint over this length of vwx. Now what is the third one? Now the pumping happens. So pumping must be the pumping can come up with two alternative options. Either we pump up the string or we pump down the string. Okay, so what it is we will see in short while. So for all I which is greater than equal to 0, so I tends to infinity starting with 0, so I is changing from 0 to infinity. Okay, so this is the condition where u, v raised to I, and w, x raised to I, and y. Okay, so this substring v and x where the pumping will happen. So what pumping means? So for consider, if I'm talking about the value of I equal to 0, so I'm talking about pumping down this string. Okay, so if I exclude this v and exclude this x, this is what I equal to 0 means. If I exclude this v, if I eliminate this v and x by considering the value of I equal to 0, what is left? I left with u, w, and y. If I pump down excluding this v and x, so resultant string u, w, and y, it should always belongs to this l. Oh, understood this? So this pumping theorem is saying if I apply a pumping down on v and x considering the value of I equal to 0, whatever string we left, it should also belong to that language l if it is a context free language. Now think about what is pumping up. Pumping up is stands for when I'm taking the value of I either 1 or greater than 1. So let's consider the value of I equal to 2. So what the string would be? So string would be this u will remain as it is. So v has to be taken twice. When I consider value of I equal to 2, the v substring has to be taken twice. If the value of I is 2, then w, then x value of I is 2, then x substring should be taken twice to form a particular string. So I have u, 2v, single w, 2x, and y, and that is that compose a particular string x, and that resultant string should always be a part of that l. Means if it is l is a context free language, so this properties should be applicable for all the context free languages. Now this is what it has been written. I'll just read it out for you. So three conditions applied. The string x, which we consider as a context free language, it will be formed by concatenating these 5 substrings. This is what we discussed just now. Now we applied a certain constraints over this substring. So length of the string vx should not be null, or it should be greater than 0, and length of the string together with vwx should be less than equal to n, where n is a constant which is depends on a particular language. Third, what we said is the third condition says we pick up two substring for pumping. What it is? The substring v and the substring x. Now why v and x we will see shortly when we'll try to prove this. We'll explain this. We'll go for proving that pumping lemma itself. So consider this is where the pumping happens, the substring v and substring x, where we can pump the strings larger or shorter. Shorter means when I consider the value of I equal to 0, I'm saying that I'm pumped down the string. When I'm considering the string, the value of I equal to 1 or greater than 1. So I'm saying that I'm pumping up the strings. So I'm adding more occurrences of V and X into X. Now, by the third condition, we are trying to say that by pumping the string V and X at 0 to infinity, we are saying that all the infinite strings are context-free languages, which is not true either. So I'm not considering all infinite strings are context-free languages. Now we have gone across to this pumping lemma for context-free languages. And what this pumping lemma for context-free languages, these are the essential properties of a context-free language. Okay, property means if I'm considering a language as a context-free language, so that language should satisfy following these conditions. It must satisfy all these conditions. Now let's go back for proof for the lemma and just read out. I'll explain what it is exactly. So to proving this pumping lemma, we have to go across few part of it. I'll explain what and how this particular string broken up into u, v, w, x, y. Why is it so, and how it should x supposed to be divided into u, v, w, x, y. Then we'll look forward to have how do you get this pumping lemma applied over v and x but not over u, w, and y. So let answer this with some few more discussion about this. So proof of the lemma, I'll read out and we'll explain this with examples. Now suppose consider grammar G is a context free Chomsky normal form. So suppose G is in the form of Chomsky normal form grammar. Let Z be a derivation tree of G. Okay, so G is a context free grammar. Through that grammar, I am deriving a particular string, what it means. And this Z has no part larger than this K. So what path specified as, if I'm taking this derivation tree right from its root to its largest path, following that path reaching to the leaf, then the string generated is a length, so that there is a bound on this length of the string. This generated string is always less than 2 raised to k minus 1. I'll come back to this later on, but just to move ahead and just see proof of this. Let G be a context, let G is in the form of Chomsky normal form grammar for L. Now consider such a particular context-free grammar. G has m non-terminals. Now I'm considering how many non-terminals I should have. So considering that Chomsky normal form grammar has m non-terminals. Okay, I'm considering this. So consider a derivation tree in G of a string in L of length 2 raised to m or more. So what it means is try to generate a particular string having the length greater than or equal to 2 raised to m. Now I'll come just elaborate this with a particular example. So what I'm saying in this is, see, consider this is a Chomsky normal form. Okay, so this now is it in the Chomsky normal forms? Yes. So what the definition of a Chomsky normal form is? So every production of this G is in the form of either of this two production rules. Single and non-terminal on the left should exactly produce two non-terminals on the right. Okay, so A's are, these are two non-terminals, so exactly two non-terminals exist. Or SA, I have this second rules even has a particular two non-terminals on the right, or this non-terminal should have exactly a single terminal on its right. Okay, so all corresponding rules following this Chomsky normal format. Now, how many such non-terminals exist? I have S and I have A. So total non-terminals are 2 in this case. Okay. So if I'm take 2 raised to m, so I'm talking about the length, it is 4. Now just to read back this statement, what we discussed just now. So we have a G in a Chomsky normal form, and let G has m non-terminals. In this right now, in this case, I am considering 2 non-terminals. So I have 2 raised to 2 particular string, that is I am trying to generate through this context free grammar. Next condition says consider a derivation tree in G. So if I derive a particular string through this starting alphabet of G of a string in L, okay, that belongs to that L, and having the let either exactly 2 raised to m characters in it or greater than 2 raised to m characters. So condition number 1, what we are saying is, if I have 2 non-terminals, okay, then 2 raised to 2 becomes 4. So I'm trying to generate a particular string having the length 4 or more. Okay, how do I get this? So you apply your derivation. So as it's starting a non-terminal, I replace this by as with this rule. Then this capital S is reapplied, or this S is can be rewritten as SA in the following format: SA. This S is replaced where this A remains as it is. Then we followed this non-terminal S is replaced by one more time by this AS. So I have ASA. Now how this can be terminated with terminal symbol? So A can be terminated with 0 and S can be terminated with 1. So I wanted to generate a length 4, so this is sufficient for me. So within this 0 or more steps, I could get this X. Now if you know context free languages and grammars, so what this X is? X is a generated string starting with this non-terminal S. So starting with this S, starting non-terminal of grammar, I could generate this X. Okay. Now if this X is derivable from this S, I'm saying X is in the language. What I'm saying, what did I say? If you could generate a particular string having all terminal symbols, the terminal symbol in this case is either 0 or 1, this is what we could derive from this S. Okay, so if anything is derivable from this S, this X, okay, so X is derivable from this S. This X, if it is derived from the non-terminal, starting non-terminal of grammar, then this X is in the language. Okay, it is always in that language for which we write this context free grammar. Now just to go back and check, see these 2 steps is similar with what we have tried. We tried this. These 2 are similar. So I have rewritten for your so I should have a parallel conversation or an explanation for this. I should not go back and forth with these pages. So if you consider this process, what this is a derivation process. So and this is what the derivation tree is. How do you get this derivation by? So I have this as S is replaced by AS, so it is represented as AS. Again, this S is represented by SA. Followed this A is terminated with 0. This S is again rewritten by AS, and following this, I could generate this 0, 0, 1, 0. So this is somehow what we wanted. It's looking like a derivation tree. And if this derivation tree is applied, so next what it says, see, if I am generating a particular string having the length 2 raised to m or greater, So exactly I'm taking about, I have in this case two non-terminals. So exactly I'm trying to generate the particular string having 4 elements, which is 0 0 1 0 in this case. Okay, then the derivation tree for x, derivation tree, this is a derivation tree for x, must have a path of length m plus 1 or more. Now what do you mean by path? So this is to consider there must exist a longest path. If I'm considering this is the longest path within this derivation tree, so in this process, in this the whole sequence, so I must have particularly a particular non-terminal should be repeated. At least a single non-terminal should get repeated. Okay, this is how we generate a particular string. So exactly what second, again try to understand this, then the derivation tree for x must have a path of length m plus 1 or more. What is m? M is right now not a total non-terminal that exists, plus 1. At least I should have within this path at least 3 non-terminals or more. Okay, and within this also few of the non-terminals of your grammar must get repeated by. So if you, in this case, if you look, this s get repeated many a times. Okay, now this whole pattern you can visualize this in this symbolic terms. So what this s is my starting alphabet of a grammar, and this is what I'm trying to generate this x by. So what I'm generating through this derivation as I'm trying to represent this derivation of x using this triangle. Okay, and in this what I need to follow is, see how do you get, how to back up this into u v w x y. So if I following the longest path within this, what is the longest path? This is has been shown, this is the longest path right from the root to its leaf. This is the longest path. Either this would be true or this would be true, because it both has the same height. Okay, now this tree has both got has the same height. So this height of the tree is 1 2 3 and 4. If you follow this 1 2 3 and 4, so height of the tree is 4 in this case. For both, either of this you can consider this. Now what I'm trying to say is, you start with this terminal symbol and follow this longest path unless and until you reach to a particular non-terminal. So we go across and check this particular non-terminal and follow this path, and this is the particular non-terminal we find out. This is capital S. Okay, now from this, once you find out a particular non-terminal, follow the same path upwards, and wherever this non-terminal gets repeated, stop there. Okay, so in this case where we need to stop, this is my first non-terminal, and following this path over this I need to stop here. Okay, now you can visualize this particular term in this sequence. So this a, which is s, what is trying to generate, whatever it generates, this is referred as w. So in this case what the particular this s is trying to generate, this is trying to generate 1. So this one is considered, whatever this non-terminal is generating, we consider this as a particular substring w. So wherever this a gets repeated, so in this case this is the particular s, and what is trying to generate, this trying to generate a particular 0 and 1 in this process, two process. So you can consider this in this case. See this, whatever it generates, it can be classified into, so we'll marks this non-terminals with this within this triangle, and see whatever this a generates, we'll write it at w. Whatever this a generate, the repeated a generates, this a means any non-terminal. It, now in this particular example it is s. So in this process this a is generating whatever substring it generates, we'll write it at v, and this substring as x, and this part we consider this as u and this part as y. Okay, now if you understood how this total x is divided into particular substring u, v, w, x and y. Now this is the particular theorem which we try to see, and why this x has been broken up into u, v, w, x and y, and from where this comes from. So after this discussion you would be clearly identified so where exactly this u, v, w, x and y came from. Now try to understand the pumping strategies. Now what pumping strategies in this context free grammar, what it says. So just don't worry about the step number 2, I'll elaborate this. Now look for this where the pumping is happening. So pumping is happening over this substring v and this over this substring x, and I is changing from 0 to infinity. Either you exclude this or you pump up this particular substring, the resultant string, whatever string you generate, it should be in the language if it is a context free language. Now let's just talk about how do you get this pumping lemma parameters v and x, how it has been chosen for pumping. So in this particular process, now just go with the discussion. Now before going across this discussion, within a few seconds, just understand this particular concept. Now what this concept is, see, I'm writing this, I'm rewriting this as, how I'm writing this as by, so s is rewritten by as. Now how this, because I have a provision inside my context free grammar. What I'm saying is my context free grammar allows me to rewrite this as by either as or sa. So because of this is happening. So this s can be written as sa because I have a s particularly producing this sa by. Why and how this s is represented by as, again the same rule is applicable. See, I have within a grammar rule s can be rewritten as as or sa, through which this derivation works. Now understanding this pattern, now look for, now you have to know what terminal symbols are in this and what are non-terminals in this. Now check this equation number 1. So capital non-terminal A, within your 0 or more step, it try to generate a W. So how is it possible? So this is possible with reference to this triangle. So this non-terminal, what it is generating this substring W in a single step. So this W is can be created by replacing this A by. Now I creating this with this reference. So this is a non-terminal and what it generates. Now the similar way, what this repeated non-terminal is trying to produce, this can be written as V, W and X. This is a 3 substring it can generate. So this A is sooner or later it will generate this V, W and X string. Okay, now with the similar, how this s is, what is this s is generating? So this s, through this s, what I can generate, the whole substring which is x, which is broken up into u, v, w, x and y. So this is s, and how did we write this? U, v, w, x and y. In stepwise approach, starting with this s, I can write this s with u, v, w, x and y. Now I hope you understand why it has been written something like this. Now going in the reverse way, this s can be rewritten as this u. Instead of writing this vwx, I can write this as capital A and then this y. So this is the next particular derivation. So this s can be rewritten as u, this part, Then instead of writing this VWX, I can write this as a single non-terminal A, and whatever left it is Y. So both are similar, okay, according to this. Okay, now what this A can be rewritten as? So this A can be, it can generate this particular V. So instead of writing this W, I can write this V, this A, and this X. So this A, which is this repeated non-terminal, can be rewritten as V, A, and X following this notational system. I can generate a V, A, and X. Now let's check how where the pumping is happening. Okay, now check this. S is deriving U, A, Y. So I'm considering this as what is deriving U, A, and this Y substring. So from sooner or later, starting with this S, I can generate this substring U, A, and Y. Now what option you have to replace this A by? So according to this grammar, this A can be replaced directly by W. This A can be rewritten by VWX, or this A can be written by VAX. Okay. Now in this case, if we choose to replace this A with the help of this notational system or this grammar rule, A can be represented by V, A, and X. Okay, so how it is possible? So this A is generating V, A, and X, so this part, and if we replace this A can be rewritten with the help of this rule. I can write this whole terminology as U, V, A, X, and Y. Now again this capital A can be rewritten with the same context free grammar rule VAX. Okay, and if I rewrite this now, if you can see this A, if once again if it is replaced by VAX inside, so where the changes are happening? So changes are happening only in terms of V's and X. So V is getting larger and X is extending. Okay, so V and X both are extending. Now this extended terminology is considered as I. So the pumping is happening over the substring V and the substring X. And where this I is, so I is a pumping constant. Okay, now consider this V. If it, when the value of I, if I select it as 0, now this part will be explained what pumping down means. In the explanation itself, we are saying that what pumping down means. Pumping down means considering the value of I equal to 0. Now starting with this S, if I could derive this as by U, A, and Y. So this is U, A, and Y. Now considering I equal to 0, so I need not have this V part and X part. Is it possible? Yes, because of this rule, A can directly produce W. So how? This A either can be replaced by this string, either can be replaced by this string, or either can be replaced this A. So A has got 3 rules. Okay, so using this A replaced by directly W, what do you get? So if I replace this non-terminal A by this W, I'll get the substring U, W, and Y. Okay, now this is what pumping down means, where we eliminated the substring V and substring X. Okay, now whatever you get U, W, X after pumping when the value of I equal to 0, okay, this string should be in the language. This is what the pumping lemma says. Now just understand the pumping lemma constraints over this. When I consider value of I equal to 0, then I need to eliminate this V and X. What is left with? U, W, and V. And if this U, W, Y, sorry, what is left with? U, W, and Y. So whatever the string is left, it should be in the language. Now this is important, and this is what we are trying to explain within this particular terminologies. Now what it is saying, after excluding this v and w, whatever the string is left, this is vwx, this string is derivable from this starting non-terminal s. Now by definition, if any particular string u w y, if it is derived from the starting non-terminal s, this is in the language. This is what context free language says. Now this is what, when I consider I equal to 0, means I pump down a particular string. When I pump up this particular string either twice or thrice, considering substring either once, twice or thrice till infinity, because I is changing from 0 to infinity, I may have now this substring which is pumped up twice. So I am considering v raised to 2 here, because v is considered, this substring is considered twice in this case. Okay, and x is considered twice in this case. So still this substring is derivable from this s. So all such strings which are derivable from s, when the value of I is changing from 1 to infinity, when I am pumping up this string v and x, the resultant string is derivable, still derivable from this s, and so that this whole string is in the language which we wanted according to the pumping lemma. What we said, according to this pumping lemma, whenever we pump up this, whatever substring you get, the language, context free language said the resultant string will be in the context free language. Now these particular explanation is good enough to know why it has to be broken up into 5 substrings and why the pumping is happening over v and x. I hope you understand this. Now just let me give you an example how to prove a particular language. So before this, showing this particular language L to be a non-context free language, we just go across this single terminology. Now up till now we have already seen what is context pumping lemma for a context free language, where pumping lemma is the essential properties of a context free language. Now I'm considering a particular L is a context free language, so that L should satisfy all these properties. What properties? Pumping lemma properties it should satisfy. Now in this case, it is just like a game. So what game it is? Now consider the language L is given and I'm trying to prove. Now consider you and me. Okay, now you are saying that this L is a context free language, and my part of the job is to prove that given L is a non-context free language by contradiction. What contradiction means? Now you have a pumping lemma in your hand, so whatever L is given, it should satisfy all that rules or properties. Now I am trying to visualize that either pumping up the given string in terms of v and x, I have a choice to replace this, either pump up or pump down this string, and I wanted to show after pumping up and pumping down this v and x, whatever string I'll get is not in the language. Now this is sufficient to prove that L is non-context free language. Now for time being we will explain this with example, but just concentrate what I'm trying to see. Now in this, see this part is this symbol represent there exist. Now in pumping lemma what we specified, n is a given constant. So I am proving the language is non-context free and you are forcing that the given language is context free language. Okay, now there always exists a particular n which is depends on the given L. So we consider this. Now we have a which we call as a universal quantifier. So this for all, this is for universally quantified. So this x I can select, but what the condition is, I can select any x which belongs to that L. What L is? L is a context free language. So I'll consider particular x which exists within a particular language. But what I'll take care of that is the length of that substring which I have chosen. I make it mandatory to have greater than or equal to the pumping lemma constant which has been given. Okay. Now again, I have there exists u, v, w, x, y. Now how to break this x within, now in pumping lemma, x is composed of u, v, w, x, y. Now as I am proving a context, particular context free language as a non-context free language, I myself cannot break this string x within this 5 substring. So I'll ask you to break and give the particular substring. So your task is to break up this given string x into any substring u, v, w, x and y. Once you break up this string, now this resultant string I'll take and I'll apply a universal quantifier. Universal quantifier, I'm able to pump up and pump down over the string by taking these two conditions also. So this all conditions are of pumping lemma for context free languages. So what this substring v and x should not be null, and the next is together vwx is should be less than equal to the given constant n. Now my my part of the job is to either pump up this string v and x and the resultant string show that this is not in the language to prove a particular language is non-context free. Just remember this, we'll take a particular example and then we'll try to prove this. Now go back to this particular example which we are trying to prove through contradiction this language is non-context free languages. So question is straightforward, show that L is a non-context free language. So what L is any particular x which belongs to sigma star, and then this pattern holds a raised to n, b raised to n and c raised to n where n tends to infinity. Okay, so this tends to infinity. So as of what we have seen, this is a straightforward pumping lemma, that is what we have applied. I won't repeat this. Let's prove L is a non-context free language. So step number 1, I should have a particular n. N means the given constant. In this case, what? So for this L, I should have a particular n which is a constant which depends on this L. So for this, I am considering a particular n is having 4. Okay, now let's consider it would have been given by u and the constant is 4. Now by giving this, I'm forming my own string. What the next comes, once the particular constant is given, now I need to choose a particular x. Okay, and what I need to take care of that, did x, this length of x should be greater than equal to this given constant n. So this is straightforward, and for this n given is 4, and then for a particular string x, I consider this n as 4 and select a particular string like a raised to 4, b raised to 4 and c raised to 4. So I have 4 a's, 4 b's and 4 c's in x. Okay, so I have chosen, and this length of this x's, I'm taking care that the length of the string is greater than see, this length of the string is greater than n. Okay, so this x I have, this is by default it is greater than 4, so it contains 4 3s are 12 characters which is greater than 4. Now what next is, now I'll ask you to break up the string. Okay, because if you see this explanation, n is given, so I can decide a particular string. Now x, now it's your point that how do you break the string up. Okay, now this can be broken up into various format. Okay, and which is a prover, I am proving this language as a non-context free language, so I won't consider myself to break this string into 5 particular substrings. So the opposite person has to break this substring into u, v, w, x, and y, and it has to be given. So as nobody's there to break this string x, so we'll consider this all the conditions where it exists. Okay, so when you're pumping, where the pumping is happening, so pumping is happening in terms of v, w, and x. Now I have all the rights. I'm considering this length of vwx where it can occur with its possible combinations. So I'm considering all such cases where this part of vwx, which is my pumping string, where the pumping will appear. Now it can appear, for time being I'll consider all such cases where this substring vwx will appear. So case number 1 is the entire vwx is in the part of a raised to n. So I'm considering within this, I'll consider this vwx should be within this a raised to n. Okay, now second possibility is this: the pumping vwx can consume few a's and few b's, so it can lie within this a raised to n and b raised to n. Third possibility is vwx can entirely lie within this substring b raised to n. So this can be within this b raised to n itself. So with this substring, I can break this vwx. It might be possible to break this vwx within this part. Fourth possible option is this vwx can entirely be in b raised to n and c raised to n. So this can either be in this part, or the last case is vwx can be broken down. We consider it as a part of that last portion. Okay, so considering this breaking up into all its varieties and considering one case at a time. Now I'll explain a single case. Rest of the things I'll leave it for you as an assignment. So what case number 1 is: length of v is less than equal to n, and it is entirely in this a raised to n. So I wanted to break uvwxy in such a way that the particular substring vwx should lie within this 4 a's. Now consider how did I break this string as. Now consider I have broken up this string something like this. Now what is happening? While breaking up the string, make sure, what I need to make sure, the pumping lemma condition number 2. What the condition number 2 is saying: if you break up this string into u, v, w, x, y, the v and x part should not be 0. Now if I break this string into something like this, I have now my substring v and x has element a and a, so this is surely not null. So I have taken care of that. Now what next is the vwx, this substring vwx, after the string gets broken up into this, I'll consider vwx, it should be less than n or less than equal to n. So in this case, what n is? N is 4. So I make sure that once you break up this string, the substring vwx, okay, consists of, it should, the length of this vwx should be less than equal to 4, and my length is 3 a's, means 3 is less than 4. The second condition is also valid. Now I wanted to go across this pumping lemma. I pump up the part of v and pump up the part of x, either by pumping up by considering the value of I equal to 0, or when I'm considering the value of I equal to 0, I'm pumping down the strings, and when I'm pumping up, I'm considering the value of I is more than 1 to infinity. Now I'll do the same terminology and I'll go for where vwx is less than 4. It is surely within the same range. Now we will show that when we pump, we want for every I equal to 0, v u v raised to y w x raised to y should be in the language. Now consider when we pump down. What do you mean by pump down? When we consider I equal to 0, then this part should be eliminated and this part should be eliminated from our substring. So if I getting across this to get particular generation, so eliminating this v and x, what is left? This a is left, so this is part of w. This v I cannot consider in this, so w I have to make sure it should be considered, and this x which contains a single a I should not consider because I am eliminating this v and x from the resultant string. So I should have this two a's only. What is left with this y should retain its values as it is. So I have 4 b's and 4 c's. Now after pumping down, what is the string is a raised to 2, b raised to 4 and c raised to 4, which is not exactly what we wanted in the language. So I'm talking about this language n, where every string should be in this format. Total number of a should be equal to number of total of b, total number of b's are equal to total number of c's. Even after pumping up and pumping down, the resultant string should be in the language, and the condition to be in the language is all a b c should have equal number of characters. Now this is what we have proven after pumping down. See, we got 2 a's, 4 b's and 4 c's, and this is clearly mentioned that total number of a's are less than b and c, and this clearly indicates this is not in the language. Okay, now no, this is contradiction. What I'm saying, this is contradiction. If the language is a context free language, I'm saying all these properties should be followed, but I'm proving that after pumping down, the resultant string which I get is not in the language, means I'm proving that the language is non-context free. Now this is for pumping down. Same condition is for pumping up. Pumping up means when the value of I equal to 2, when this substring v is taken twice, so this v contains a single a, so I'm considering value of v twice, so a should be repeated or considered twice, and this x which is single a should be considered twice to form a particular string. So what the resultant string is? So resultant string is says when the value of I equal to 2, I get this v as is taken twice. So these two alphabets are taken twice and this x are taken twice. Rest of the part u, w and y remains as it is. So what the resultant string we get? This is a raised to 6, b raised to 4 and c raised to 4. When I pump up over a particular substring v, when the considering the value of I equal to 2, the resultant string should be in the language, but I won't see that case in this. So I have 6 a's, 4 b's, 6 c's, which is not in the language, which we are trying to prove that it's a context free language. The language which we are trying to prove is all three should have equal number of a's, b's and c's even after either we pump up or pump down. Okay, it belongs to this, means I'm expecting to have the resultant string should have equal number of a's, b's and c's. Now you clearly it is mentioned with this example that after pumping up and pumping down, we won't get the resultant string in the language. So with contradiction, I'm proving that this language L, which I'm saying, is surely not a context free language. Hence we have proved. Now you can follow the case number 2, where we break down this substring in this a raised to n and b raised to n pattern. So if we consider this, so we break down something like this. So v contains this a, so this vwx should lie within this boundary. A raised, some part should lie within a raised to n, and some part should lie within b raised to n, and still we can prove when I equal to 0 over the string. Okay, over this, after this condition, if we pump down by eliminating this v and this x, what is left? This u as it is, v and x eliminated, this w and rest of the part of my y. So this is the resultant string which I get, which having a raised to 3, b raised to 3 and c raised to 4. In this case also I am getting the total number of a's and total number of c's are not equal. So after pumping down with case number 2, I am having this resultant string which is not in the language. When you pump up this, it will have the same result over the string. If I pump up this v part and x part, considering twice, I'll get this particular string, and after counting it, I have a raised to 5, b raised to 5 and c raised to 4. So total number of a's and b's are same, but c's are more less than your a's and b's. So surely this is not in the language. So I'm proving in case number 2 that the language is non-context free language. Now the third case is this VWX should entirely lie within this b raised to n part. So considering this b part, and surely if this is this v and x, considering value of I equal to 0, if we break up, you will get a particular string, and this is a raised to 4, b raised to 2 and c raised to, which is not in the language. Same when we pump up this, considering, we'll get a particular string a raised to 4, b raised to 6 and c raised to 4, which is a and b and c, these three are not equal. So this is not in the language. Now case number 4 is entirely, we are considering this VWX is lies within the second half of b raised to n and c raised to n. So when you consider this, after pumping down, we'll get this resultant string. Now you are good enough to how do we get this string? You all might have the clear understanding of it. So after producing this, eliminating this v part and c part, if I resultant string, if I put, I'll get 4 a's, 3 b's and 3 c's, which is not in the language. So all three are not equal. Last part is when we pump up, we'll get this particular string where we find a, b, c's are not equal. So these are not in the language. And what the last pattern says, when you try to break up this VWX is lying entirely within this last half, which is exactly at this c raised to n. So pumping down will result me this, where I have less number of c's as compared to a's and b's. So this is not in the language. And if you consider this pumping up, when considering I equal to 2, you have a raised to 4, b raised to 4 and c raised to 6. So you won't have a, b and c, both three are equal. So this is not in the language. So the conclusion is simple. For all 5 cases, we have proved if we pump up or pump down the strings at v and x, considering the value of I is changing from 0 to infinity, does not satisfy the pumping Lemma criteria for context-free languages. So we can say that the given L is non-context-free language with effect, as this is after following the, so this is controversy. So with contradiction, we are proving what the language should hold all the properties, and these properties are not satisfied by this given L. So we are saying that this L is non-context free. I hope you understand how did we started with and how did we come up with this conclusion that the particular string is or language is non-context free language. Thank you.